Okay, we're going to have a look at worksheet 4, which is the one entitled Algebra Part 3. Let's have a look at question 1D. And question 1 is where I'm asking you to rearrange the equations to make x the subject. So 1D is the cube root of y over x minus 4 equals 3 lambda, that's that Greek symbol, plus 2. Now, as with all of these things, the first thing you want to think about is how can I get the x by itself? And at the minute, the x is trapped within this cube root term. So the way that we undo a cube root is to cube it. So we cube both sides. So let's just write that out in full. Now, remember, another way we can write the cube root is like this, to the power of a third. So we're going to cube that, and then we're going to cube this side as well. Okay, and if you remember from rules of powers, if we're faced with something like this, we multiply the powers together. So a third times 3 is 1, so therefore those cancel out. Okay, so then we're left with y divided by x minus 4 equals 3 lambda plus 2, all cubed. Now, we don't want the x on the bottom, we want the x on the top. So one way we could do that is multiply both sides by x minus 4. So for the minute, we've got to treat this as one thing because it's underneath it's the denominator of this fraction. So let's do that. Let's multiply both sides, and I won't go through and show it all, but basically multiplying this side by x minus 4 means that that will cancel out, and effectively we're bringing it up here. So then we're left with y equals 3 lambda plus 2, all cubed, x minus 4. Okay, now we can isolate this bit by dividing both sides by 3 lambda plus 2 cubed. So again, I'll just write that out like this. And now we're left with something hopefully a bit quite straightforward. So the last step is just to add 4 to both sides, and then we'll have x by itself. So finally, I'll just write that over here. Y equals 3 lambda plus 2 cubed plus 4 equals x, and that's how we do that one. Okay, let's have a look at question 2. Question 2 was about finding some common factors to see how they work. So question 2b, we'll do that one because that's a nice and straightforward one for you. So 17p plus 34. So I guess this is asking you to know your 17 times table, or at least realize that 34 is 2 times 17. So for that, what we can do is take out 17 outside of a bracket and put in p plus 2. So 17p plus 34 is exactly the same as this. If we multiply out the brackets, we get 17p plus 34, 17 times 2 being 34. Okay, that one's pretty straightforward. Let's just try one that was a bit more complicated. Let's have a look at question 2c. So that one is 4x plus 2xy squared plus 10x y squared z. Okay, so looking through this, we can see some common factors here. We've got all even numbers, so they're all going to have a common factor of 2. We can't go any higher because 4 won't go into 2 and 4 doesn't really go into 10, or at least not with a whole number. So we can take out 2 outside of our bracket, but we can also see there's an x as well. So that's the first thing to start off with, because this is common to everything. So we can say, okay, 2x. Now, if we divide this by 2x, we're left with 2. 2x times 2 is 4x. So that's how we map that back onto there. Here, this one's a bit more simple. So 2x times y squared is 2xy squared. So that just becomes y squared. So when we multiply that, we get that. And then here, if we're dividing this by 2x, we have 5y squared z. So if we're going to multiply these out, that becomes 4x, 2xy squared, 10x y squared z. We could go a little bit further if we like here, just with these two terms, so we can factorize this. So 2x, 2. Now these both have a common factor of y squared, so we could take y squared out of the brackets, and then that becomes 1, because y squared times 1 is y squared. And then here, we've just got the 5 and the z left. And then we close those brackets like that. So that would be factorized and factorized twice. And we can always double check to make sure that what we've done here expands, that's what we call that, multiplies out of the brackets to give us back to here. And I'll leave that as an exercise to you to make sure that that works. Question 2D on here is a bit like the complicated one that was at the end of the last worksheet. Okay, we'll have a quick look at question 3. So the first part of question 3, well, okay, we'll do question 3C, but we'll say a little bit about question 3B as well. So question 3B is gives you a value which you're going to need to use in question 3C. So there I tell you that the volume of the Earth is 1.1 times 10 to the 12 kilometers cubed. Now we're going to have to do a little bit of unit manipulation here, and we'll come to that. Okay, so in question 3C, I tell you that the density of the Earth, and we just call that D here, is 5,500 kilograms per meter cubed. Okay, then I say, well, what is the mass? Now, we can look at the units of density. We can say it's kilograms per meter cubed. And that tells us, another way of writing those units would be is kilograms over meter cubed, right? So in there is the formula for how we calculate density. It's mass divided by volume. Okay, so let's write that out. Mass divided by volume, m over v if you like, equals density. Okay, so if we want to rearrange this to make mass the subject, we just multiply both sides by volume. Then the volume here will disappear and we'll be left with m for mass equals d times v, density times volume. Okay, let's come back and think about our numbers now. So we can say, okay, so mass is going to equal our density, 5,500 kilograms per meter cubed, times, dot we can use in place of times our volume, which is 1.1 times 10 to the 12 kilometers cubed. We go, oh, hang on a minute here. We've got volume in meters cubed, and here we've got our volume in kilometers cubed. So we need to convert this into meters cubed. So let's just have a think about how we're going to do that, and I'll switch to a clean sheet of paper in a second. So how do we go from kilometers cubed to meters cubed? We know, at least I think we all know, that 1 kilometer is the same as 1,000 meters. Now a kilometer cubed is going to look something like this. Very big. This is my 3D box. We've got 1 kilometer along this bit, 1 kilometer along here, and 1 kilometer along there. Okay, so 1 kilometer by 1 kilometer by 1 kilometer, 1 kilometer cubed. If we convert that into meters, that's 1,000 times 1,000 times 1,000. So 1 kilometer cubed equals 10 to the 3 times 10 to the 3 times 10 to the 3 meters, 10 to the 3 being 1,000. Remember our rules for working with powers. So this would be 3 plus 3 plus 3. 1 kilometer cubed is 10 to the 9, meters cubed. 1 billion meters cubed. So it's huge, a huge amount. So we can use this number here to help us convert this into something we can use in our equation. So we always want to make sure that our units match up, and our units need to cancel out, and we will do more about that next time. So if we're back to our equation, we've got, so the mass equals the density, which is 5,500 kilograms per meter cubed, times our volume, which is 1.1 times 10 to the 12 kilometers cubed. But now we need to convert this into meters cubed, and our conversion factor from before is we multiply that by 1 billion. Okay, so 10 to the 9. We've got 10 to the 9 meters cubed per kilometer cubed. Okay, there are 1 billion meters cubed per kilometer cubed. So we can give this conversion factor units, and that helps us out. Because then we can go through and cancel this. We can see we've got kilometers cubed up here, kilometers cubed down here. That cancels out. We've got meters cubed down here, meters cubed up here. Those cancel out, so we're left with kilograms. So this makes sense, right? Because we want mass has the units of kilograms. And that's what we want. So we just multiply these numbers. So that's 5,500 times 1.1 times 10 to the 12 times 10 to the 9. And if you stick those into a calculator, you should get something like 6.1 times 10 to the 24 kilograms. And that's the mass of the Earth, or at least our estimate of it, from going through that calculation. I'll quickly say something about question 5, which is asking you to think about units for things. This is really just to get you thinking about how we translate words into something usefully mathematical. So I'll just say a bit about just question 5a, and we can talk about the others during the workshop. So there I ask you for what would be the units of a conversion rate if we were going from pounds to dollars. So British pounds going to dollars. What do we need to know there? Well, we need to know dollars per pound. Okay, so the conversion rate, let's call it X. So X would have units of dollars per pound, or we can write that equivalently as dollars per pound. And this makes sense using the same kind of logic we've talked about there. So imagine if we've got like 10 pounds, I'll put the units there afterwards. And if we multiply that by a conversion rate, let's just make one up, 0.8 dollars per pound, we can see that the pounds cancel out and we're just left with dollars. So 10 times 0.8 would be 8. Okay, so £10 would be $8. I've got the conversion rate slightly the wrong way around there, but hopefully you get the point for what I was talking about. All right, good luck with the rest of those, and we'll talk about some more of that during the workshop time.